This next section we're going to talk about is section 7.3 in your book. Before you get started watching the video, you really need to read the section in the book and also read the first half of the page of the notes that I gave you. So we're going to start about halfway down the page. I'm going to assume you've already read all that. So what we're going to be talking about is how to find the volume of odd-shaped things. When we were in geometry or even in elementary school, you had formulas for volume of a cube and a prism and volume of a sphere or a cone, things like that, that you had a formula for. And all those formulas actually were derived using calculus, and we're going to come up with a method to use to find the volumes, which will work for those, but will also work for shapes that are just weird shapes that you can't necessarily use those formulas, even like a donut and things like that. So what we have to start with is figuring out, when we did areas of a curve, we used little slices, little rectangular slices, and we added them all up, and we remember that the definition of an integral, we have an integral of a function, then what that is, it's a limit of Riemann sums. Remember, the sum as k goes from 1 to n of f at x k times delta x k. So we added up this area of all these little rectangles, length times width, and added them all up as we got more and more and more rectangles, or as our delta x got smaller and smaller and smaller. And what we found was that limit was an integral, and we could use antiderivatives to find that. Well, we can use that same technique that we used for area, we can use for volume. But instead of taking rectangular slices, we're going to take little slices that can look something like this. Little shapes that we know how to find the volume of, and we're going to add the little slices of volume up to get the total volume. So the first thing we need to look at is kind of remember how to find volume. And this is a prism. There's a picture of this on your notes. And this is one of our slices if we have a shape that is going to cut off where the sides are square. So to find the volume of the slice, remember the volume of a prism is length times width times height. So we have our length times our width times our height, however, whichever order you want to put that in. So the volume of this particular slice is x squared dx. Now the thing that you're going to notice is on all our slices, just like when we had our rectangles, the width of our rectangles was dx, or if we went the other way, it was dy. We're going to have the same thing here with our slices of volume. Now what happens if our slice of volume is a different shape? Let's say it's semicircular. So there's a picture there on your paper, and it's going to be a lot better than what I can draw here. But you have this semicircular slice, something like that. Its width, again, is dx, and this time we have this diameter of x. Remember, the volume of any kind of prism is the area of the base times the height. Before, on the last example, we had a rectangle, so we had length times width was our area of our base. So we just need to find what the area of the base is. Well, this is a half of a circle, so half of a circle is pi r squared. So half of a circle, half times pi times what's the radius? Well, the radius is x over 2 squared, and then our height is dx. So when we calculate this all out, we've got pi over 8, because we've got 2 times 2 squared, and then times x squared dx. Now it's going to be really important that you think about how to do this, because when we find different volumes, for example, if we have like, sorry, I keep hitting that button. We have, for example, if we have a cone, it's a terrible drawing, but you get the idea. If we have a cone and we want to find the volume using this method, then when we cut off our little slices, we're going to have little discs. So the area of the base would be a circle, and then times the height, dx. Or if we have a shape that looks like, let's see, I can't think of one like that, but if we have a shape that looks like this, then when we cut off a little slice, our little slice is a triangle. So you're going to need to remember the area formulas for triangles and the different kinds of triangles, for circles, squares, rectangles, those kind of things. Today we're just going to talk about the volume of areas with known cross sections. We'll talk about some other methods in other lectures, but today we're going to use the ones for these known cross sections. So if you look on the back page of that first of the notes, you'll see two examples there, and let's go over those. First example says the base of a solid is the region enclosed by the graph y equals negative x, the coordinate axes, and the line x equals 3. All right, so let's see what that looks like. Now, key to all of this is going to be your picture. You have got to draw a picture. You cannot get away with not drawing a picture. So when we draw this, we see we've got y equals e to the negative x. So that's this way. So this is y equals e to the negative x. And then we're going to have the line x equals 3. So we've got 1, 2, 3. And then the coordinate axes. So the area we're looking at here is this one here. And you say, well, but we're looking for a volume, aren't we? Because that's what we're talking about, volumes. Well, what does it say? It says the base of a solid is the region enclosed by the graph of y equals e to the negative x, the coordinate axes, and the line x equals 3. If a plane cross sections perpendicular to the x-axis are squares, then what is its volume? So that wording is what's going to kind of trip you up. So you're going to have to think about this. All right, we've got our area. This is the base of our prism. The base of our prism is this weird shape here. What we have then is perpendicular to the x-axis. So coming out of the page, we've got these squares. So what that means is we have this shape that looks something like this. We've got these squares, and it's got this little curved thing coming out of it until it gets down to another square at x equals 3. So we have this shape that looks like this, with these curved sides here. And then it's squares all along. So we can slice off individual squares in here. I know it doesn't look like a square, but sorry. So we slice off these individual little pieces that are squares. So what do they look like? Well, what that's going to look like is we're going to have these pieces that are squares, little slices. You can think about this, it's kind of a smushed bread loaf. We took our bread loaf and we set a gallon of milk on it in the bag, and it's smushed. And so we have all these pieces, little slices coming along. So our width we know is dx because we're cutting the slices where the width is pieces along the x-axis. So our width here is dx. But then we need to know what our side lengths are. Well, it says that the plane cross sections perpendicular to the x-axis are squares, so we know that they're equal length. But we also know that what is this? Need more colors. What is this height here? What is this length here? Right, it's the function itself. So this height is e to the negative x, and because we know it's a square, then we know its width is going to be e to the negative x also. So we have each of these little slices like this that we're going to find the volume of. So what is the volume of this little slice? Well, the volume of the little slice is e to the negative x times e to the negative x times dx, or e to the negative 2x dx, which means that you have individual slices with this volume, and if we want to add them all up from x equals 0 to x equals 3, then all we need to do is take the integral from 0 to 3 of this volume, and we're adding it all up. So we add it all up, and we have to use our u substitution. U is negative 2x. So du is negative 2 dx, which means I need a negative 2 in here, which means I've got to have a negative 1/2 out here. So I rewrite my integral. I've got negative 1/2, the integral of e to the u du, and negative 2 times 0 is 0. Negative 2 times 3 is negative 6. Calculate this out, and I've got negative 1/2 e to the u, because the integral of e to the u is just e to the u, from 0 to negative 6, which gives you negative 1/2 times e to the negative 6 minus a negative, so plus 1/2. E to the 0 is just 1, so here is our answer, and you can get that in a decimal if you want. But if you look at your paper, it's not in, the answers aren't in a decimal. This is answer A. So what do? We found a slice, the volume of one slice, and then we used our integrals because we know that definition of an integral is Riemann sum and adding up of the little areas. So this time we're adding up little volumes, but an integral is just adding up little pieces. So we take our integral from 0 to 3 of this piece. Now, I want you to try the second example on your own, and pause the video and go ahead and do that. Alright, so you should have gotten a picture that looks something like this for your base part. And then the cross sections are square, so again we're going to have this square area with the sides that look weird. I know this is a lot of drawing, but it will really help you a lot if you actually draw all these pieces out. So our slice looks like this with a dx. You should have gotten that your side lengths were 4x squared, the function. And since we're going from 0 to 1, we take the area, or the volume, which is 4x squared dx, which is the integral from 0 to 1 of 16x to the 4th dx, which is 16 over 5x to the 5th, evaluated from 0 to 1, which is 16 over 5, which is d. So hopefully you got this one on your own. If you had a little trouble with it, go back and look and check your work. We'll do some more examples in class and look at other methods on other lectures. Make sure you've read this section, written down any questions that you have.